Okay, so section 8.4 is titled Normal Distributions. We're spending the first day going through these breakdowns within a normal distribution and using that to predict percentages of data that falls between values. And then we'll start to compare and evaluate data values using something called Z-scores. So the empirical rule is a property for the normal distributions where the approximate percentage of data values falling in any interval of the range of the data can be determined using the mean and the standard deviation. So what this is telling us is that about 68% of all data values fall within one standard deviation of the mean. So if the mean is here in the middle and I add a standard deviation to each side, that 68% of the data is falling within that range of values. And then 95% of the data values fall within two standard deviations. So if I have the mean and I add and subtract the standard deviation twice, whatever those numbers are, 95% of the data values fall within those two standard deviations. This is what we're going to call a reasonable interval. Sorry, a reasonable range of values in future sections. So that's kind of the key, is that if I know 95% of the data fits between two numbers, then it's a pretty good idea that in my study that the actual mean that I'm looking for fits between those values. And then about 99.7% of all data values fall within three standard deviations of the mean. So that means that if I take the mean and I add the standard deviation 3 times and I subtract that number 3 times, that pretty much all of the data will fit between those two numbers. So what we're going to use this for is to make some predictions. So we are given that the mean plus and minus one standard deviation holds 68% of the data. So if I think about breaking this up, because I will ask questions about certain values. We're going to look at what percentage of data fits essentially between each of these lines. So what percentage we can find within each of these sections. So we're going to start looking at the 68%. So if this is half of the 68%, that means that 34% of the data is going to fit between those two values. And then if we think about the rest of that, so ultimately for this section here, if this was 68% between the mean and one standard deviation, and the mean and two standard deviations is 95%, we can figure out what these values are by finding that difference and cutting that in half. So if I were to do, just on the side, 95% minus 68%, and so calculating that value will tell me what the two together are. And then if I divide that number by 2, then that's going to give me the value for each one individually. So if I do 95 minus 68, that's going to represent 27% of the data. So this section and this section are 27% of the data. So if I want to find just one of those, if I divide that by 2, that's 13.5%. So let me just find another color. So this would be 13.5% of the data fits between 1 and 2 standard deviations. And then finally, we don't necessarily check the value between the mean and 3 standard deviations. So technically, if I wanted to find that, I would do 99.7% and subtract the 95%. So 99.7 minus the 95 is 4.7%. So that would mean that this section and this section are 4.7%. So if I divide that by 2, that's 2.35. So that means that this section here is 2.35% of the data. And then that further section would be the rest of that value to make 100. A number that's used more is past 2 standard deviations. That would represent 100%. So if I'm doing the same thing, but I'm doing 100% minus the 95%, that gives us 5%, which means that both of the red arrows represent 5% of the data, so they'll each be 2.5% of the data. Another thing to remember is that the mean splits the normal curve in half. So that means that if I think about this mean as a dividing line, that 50% of the data is on either side of the mean. Okay, so that means that if I were to take the 34, 13.5, and the 2.5, again, this 2.35 isn't a number that we use very often, that should give me that 50% to represent the 100. So ultimately, these values are something that you will need to know, especially if you're going to take a stats class. So this will be one of the first things that you kind of start to work with. And so within these problems, what will be given to us is simply the mean and the standard deviation, and we'll ask questions about what's within the data. So when I'm given a problem where it's talking about a normal curve, my first step is always that I want to draw the normal curve so that I can see what these values are. So when drawing a normal curve, we're going to draw a number line. That number line is always going to have 7 lines. So the middle line represents the mean of the data. And then to find the other lines, I'm going to add and subtract the standard deviation multiple times. So if the mean is in the middle, I'm going to add the standard deviation 1, 2, 3 times. I'm going to subtract the standard deviation 1, 2, 3 times in order to get the values that represent this normal distribution curve. So the numbers are what's important, not necessarily how you draw the curve, because obviously mine does not look symmetric. So we have an example of an early application of statistics was in the year 1817. A study of chest circumference among a group of Scottish men established an approximately normal distribution. Their chest circumferences ranged from 33 to 48 inches, with the mean chest measurement of 40 inches. So they're giving us the mean is 40 inches. So we're going to put 40 as the value for the mean, and a standard deviation of 2 inches. So we're going to use the empirical rule to help us understand the distribution of chest circumferences in the study. So what they're telling us is that I'm going to add and subtract the number 2 to get the rest of my values. So 40 plus 2 is 42. Okay, so I'm doing mean plus 2. 42 plus 2 tells us that the next value is 44, and then the mean plus 3 standard deviations, so plus 2 again, is going to give us a value of 46. Then we're going to do the same thing on the other side, except instead of adding, we're going to subtract the 2. So 40 minus 2 is 38, 38 minus 2 is 36, and then 36 minus 2 is 34. So this is the normal distribution. Again, I'm not necessarily going to draw that steps every time, right? So underneath this dotted line is really just so that you can see what's going on for this first time. I won't draw them further from this. So what range of chest measurements contains the 68% which fall closest to the mean? So if we look at the empirical rule, 68% fall closest to the mean. They're 1 standard deviation away. So that means that we go up one and we go down one to find the middle 68%. So within this value, since the mean is 40, one standard deviation above is 42 and one standard deviation below is 38. So this is going to represent 68% of the data. So it's between 38 and 42 inches. What would you expect the chest measurements to be for the 2.5% of men with the smallest chest measurements? So smallest is going to be on the left side of the mean. And if we look at the 2%, the 2.5% is anything below 2 standard deviations. So looking at the empirical rule, 2.5% represents below 2 standard deviations. So I'm just going to say below 2 sigmas. And so on the graph, if the mean of 40 is here, then we had 38. 2 standard deviations was 36, and so it would represent that rest of the graph after 36. So it would be 36 inches or less would represent the smallest 2.5% of chest measurements. So again, I'm really just referring back to this each time. So looking at the middle 68%, that told me that I'm looking at from the mean, I'm going out one number to find what represents that full 68%. Okay, so I'm really using this until I know it for these problems. So this is something that we will refer to for every single problem. Okay, so this is what we're looking back at to answer the questions. So recent SAT scores for college-bound seniors are normally distributed with a mean score of 508 and a standard deviation of 121. How does the empirical rule help you understand the performances of individual students? So we always want to start with drawing a normal curve. So we're going to do mean and then 1, 2, 3 standard deviations on both sides. And again, the shape of the curve isn't what matters. It's really just matters what the number line looks like. So the mean goes in the middle. So our mean score is 508. And then standard deviation is 121 points. So that means that from 508, we're going to add 121, which is going to give us 629. Then we're going to add 121 again, which gives us 750. We're going to add 121 a third time, which gives us 871. So that means that 99.7% of the scores fall below 871 and above whatever number we're going to end up with here. So then from 508, now we're going to go backwards. So remember on this side, we were adding 121. And then to get on this side, we're going to subtract 121. So 508 minus 121 is 387. Minus 121 is 266. Minus 121 is 145. So again, the empirical rule tells us that all those percentages are true for a best estimate. So that means that 99.7% of people that took this SAT scored between 145 points and 871 points. What proportion of students received scores between 387 and 629? Okay, so if we're looking at this, these questions are backwards from the questions that we looked at on the last problem. So the mean is 508, 629, and 387 are one standard deviation from the mean. So that's that first number in the empirical rule. So that means that 64%, sorry, not 64, 68% of the scores lie between those two numbers. So 68% is between those first two lines on the standard, on the normal curve, right? So if I'm looking at mean plus and minus 1 standard deviation, 68% is the answer. For B, what proportion of students receive scores greater than 387? So if we look at this, 387 is 1 standard deviation below the mean. So what we can think about here is, I know that this portion is this portion here, that's that 34%. So that means that 34% of the data fits between the 387 and 508. What I also know is that the rest of the data is half. So everything to the right of 508 is 50%. So all the scores greater than the mean, right, represents 50% of the data, plus that 34% of data that lies between the mean and the standard deviation. So that means that this is going to be 84% that is greater than 387. Okay, so ultimately with questions that involve the empirical rule, all that you're doing is drawing the curve and then matching your numbers to the locations and the values that we have on this highlighted empirical rule curve to find the values. So know that you won't be given this if you were tested on it. So make sure that you practice it if that comes to be the case. And then you are expected to know that for future courses. So then the last thing we're going to talk about today is Z-score. Z-score is the number of standard deviations a data value is above or below the mean. So you can use Z-scores with any distribution. In general, if I was talking about 629, since I added the standard deviation once, that would have a Z-score of +1, versus 387, I subtracted sigma once, that would give me a Z-score of -1. So then 266 would have a Z-score of -2, -3 for 145. 750 would be plus a +2 Z-score, and 871 would be a +3 Z-score. So Z-scores are more for numbers that are not perfect standard deviations away from the mean. The equation that we will use to find the Z-score is taking the data value that we're given, asked about, subtract the mean, and divide by standard deviation. In symbols, that's x minus mu over sigma. So for each of these, if I want to find the Z-scores to compare, I'm able to compare apples to oranges. So what I mean by apples to oranges is if I'm taking the SAT and you're taking the ACT and we want to see who did better, we can do that if we know the average and the standard deviation of those tests. So then we can see who did better compared to the rest of the students that took the test. So Ella and Alicia are comparing scores on their college entrance exams. Ella's SAT score is 1380. Alicia's ACT score is 32. The mean SAT score is 1,000 with a standard deviation of 200. The mean ACT score is 21 with a standard deviation of 5. So who has the better score? So we're looking at, in relation to the average, which person performed better, because the numbers are not near each other. So let's look at Ella first. So her data value is the X. So X is her score. Her score was 1380. The mean score for the SAT, that's what she took, is 1,000, and the standard deviation for the SAT is 200. So to find her Z-score, we're going to take 1380 minus the average score, which I accidentally wrote as 100. That was supposed to be 1,000. Divided by the standard deviation of the scores, which was 200. So we're taking 1,380, subtracting 1,000, dividing by 200. That gives us a value of 1.9. So the z-score for Ella is 1.9. What this means is that if this is the mean, this is 1 standard deviation, this is 2 standard deviations. That means that I use red for Ella's name. That means that Ella's score is here. Let me finish drawing out. So it would be 3 standard deviations. So 1, 2, 3. So on a distribution curve, we're looking at comparing apples to oranges, so SAT to ACT. So now we've got Alicia. Alicia took the ACT instead. So for Alicia, her score is 32. So in the z-score formula, we're going to use 32 for her score. The mean for the ACT was 21. And the standard deviation for the ACT was 5. So sigma is 5. And so if we plug these values into the formula for z-score, her z-score is 32 minus 21 divided by 5. So if we calculate that, that gives us a value of 2.2. So that means that Alicia's score is 2.2 standard deviations away from above the mean. So if this is 1.9, 2.2 would be about here. So that means that Alicia did better because she's further to the right on the entrance exam. Okay, so Alicia's ACT score is better than Ella's SAT score based on looking at the z-scores of the two. For the final problem on here, we are looking at scores in card games. So they're playing hearts and 5 crowns. And this time, though, they give us the z-score, and they're asking us to compare the means of each game. So for this problem, we've got Keith, who's playing hearts. So let's write his name. And so his score is 81. So his value for X is 81. And then we have Bruce, who's playing 5 crowns. And his score is 216. So what they're telling us is that they got the same z-score. So the z-score for both players is 1.3. So that means that they did the same in terms of each of their games compared to the mean. But the standard deviation in hearts, so sigma for hearts, is 7 points, and the standard deviation for 5 crowns is 28. So they're asking us to compare the means. So if I think about the formula for z-score, this time we know z, we know that we're starting with 1.3. So for Keith, we're going to do 1.3 equals his 81 minus the mean is what we're looking for, divided by the standard deviation, which was 7. So if I want to solve this for the mean, what I have to do then is get rid of the 7 and then get rid of the 81. So in order to isolate mu, or the mean, I'm going to have to multiply both sides by 7. So I get 9.1 is equal to 81 minus the mean. And then I would subtract the 81. Oops. So if I subtract 81 from both sides, I get negative 71.9 is equal to negative mu. And so since they're both negative, technically I'm dividing by a -1. So the mean for hearts is 71.9. And then we want to also find the mean for 5 crowns. So we have to follow that same process. So this time the z-score is still 1.3. But that's equal to Bruce's score, which was 216, minus the mean we're looking for, divided by the standard deviation of 28. So the process is the same when I'm solving for the mean because I know the same two pieces. However, I'm multiplying this time both sides by 28 to get rid of the denominator. So 1.3 times 28 is going to give us 36.4 is equal to 216 minus the mean. And then if we subtract 216 from both sides, that gives us that negative 179.6 is equal to the negative of the mean. So that means that the mean for 5 crowns is 179.6. So remember that the first part of this lesson is knowing and applying the empirical rule. So knowing the 68, 95, 99.7, and then being able to kind of break down that distribution to answer a question about something that is approximately normal. And then the last part was finding a z-score to compare values or to solve for values. So the z-score formula is in that